What's up guys, it's Simon Fiaz and today's video is on AQA A-Level Chemistry Paper 2 2020. Question 1. Use the graph in figure 1 to determine the initial rate of reaction for this experiment as stated to units. Initial rate units. Okay, so initial rate of reaction of the experiment. So I'll go to 0, time is equal to 0, and I draw a tangent. And then I just do y2 minus y1 over x2 minus x1. So I'd say 125 minus 0 over 40 minus 0 from my graph, which will give me 3.125 units centimeters cubed as to the power minus 1. Look at the mark scheme. Centimeters cubed s to the power minus 1. Perfect. But it says allow 5 to 7. So I've clearly done the tangent wrong. So let's try it again. Tangent drawn at 0. .5. The reason, obviously, in the exam you would be able to way easier to draw a straight line through paper compared to on a screen like this. Yeah, so I go up to this is the initial rate. It's going like this. I go here, then I just draw like a tangent here, and then work it out. Okay. My apologies for this part because obviously this is not great. I didn't get this because it's better to be done on a piece of paper, these graph questions. Anyway, let's carry on. Question 1.2, state the relationship between the initial concentration of phosphonate ions and T. Well, phosphonate ions and T, I can see that it's proportional. So yeah, H2PO2 squared proportional to 1 over 2. O2 minus squared proportional to 1 over T. The order is obviously going to be 2. Reason being is because if I look at this, the initial rates of reactions, and I can see that, look, I go from 4 to 16, 34, 64. Yeah, so H2PO2 minus squared is directly proportional to 1 over T. Orders 2. Complete the diagram show the hydrogen gas should be collected and measured in experiments in question 1.1 and 1.2. There you go, and then this should be something here to attach it onto, and then you've got here your gas syringe, and then you've got like your what's it called, stopwatch. That's not really relevant though for this. And then your axis, so I'm just showing it like this, like 0, 5, 10, 15, 20, 25, 30, for example. And yeah, that's it. Reduced overall effect on the rate equation when concentrations of both L and M are halved. Well, if L and M are halved, it's going to be a half times by a half squared, which is what? A half times by a quarter. So rate is, well, it increases by, because I'm timesing it by 1/8 now. So it basically, if I do 100, so it decreases by a factor of 8. Decreases, since it's 1/, decreases by a factor of 8. There we go. Oh yeah, and you oh, it didn't actually tell us to what's it called? Label it, but yeah, conical flask and reaction mixture. So that's your conical flask. That's your reaction mixture, and this is obviously measured volume gas given off using a gas syringe. Conical flask, reaction mixture, and for this one, falls by a factor of 8. Yeah, rate decreases by a factor of 8. Calculate concentration M if the rate constant is 21.3. Okay, so it said the rate reaction is this. When the concentration of L is that, calculate concentration M is the rate. If the rate constant is that, and I'm using KLM squared, so rate equals K concentration of L times by concentration of M squared, right? And I want to find out concentration of M. So it's going to be rate divided by K times by concentration of L equals concentration of M, and obviously square root of that equals concentration of M, which is going to be square root of 21.3. No, sorry, that's the rate constant. The rate of reaction is 0.0250 divided by 21.3 times by 0.0155. So square root of 0.0250 divided by 0.0155 times by 21.3, and I just pressed the cancel button. That's great. So 0.0250 divided by 0.0155 times by 21.3, 0.275. 0.275, perfect. A definition question, but to look at them asking for this one, overall order of reaction. The sum of powers to which the concentrations are raised in the reaction equation, in the rate equation. The sum of the powers to which the concentration of reactants are raised to in the rate equation. Concentration of powers to which concentrations are raised. Concentrations are raised in the reaction rate. Why do I keep saying reaction in the rate equation? Question 2: draw a circle around any chiral center. Definitely this, because that's 1, that's 2, that's 3, and then that's 4. Yeah. Identify the functional group in a prialocane molecule. Take the boxes corresponding to the functional groups. So it's going to be your amine and your amide, not your ester or ketone. Amine and your amide. Draw a structure of 2 organic products forming complete hydrolysis prialocane in acidic conditions. So we have to look at the ester link, which is here, cut the S link off, and then I've got this NH3 plus, yeah, that's one of it. Sorry, the S link is here, not there. Or the amide link, cut that off, you get NH3 plus, and then the rest of it is just going to be C double bond O. You got C double bond O, and then you've just got your OH, and your CH3, NH, CH2, CH2, CH3. So yeah, the only thing I added was two H pluses here and positive charge, and here all I added was the OH. Because remember, in the hydrolysis we're reversing the condition. So what happens is, this is where the hydrogens come from, the H2. So these two are hydrogens and the oxygen in this case. Then it says, explain how structural feature of this enzyme enables it to catalyze hydrolysis of isomer G, but not the hydrolysis of isomer F. The idea that enzyme first has an active site. So yep, enzyme has an active site, and the idea that the G enantiomer has the complementary shape. The G enantiomer has the complementary shape, and that's why structural feature enables it to catalyze hydrolysis of isomer G but not hydrolysis of isomer F, because it has an active site and G enantiomer has a complementary shape, whereas the F and dash enantiomer does not have the complementary shape. Question 3: identify the isomers that would react when warmed with acidified potassium dichromate. Okay, just 1 second, guys, and I'll get back to it. Perfect, let's go to it now. So, identify the isomer that would react when warmed with acidified potassium dichromate. Okay, or the isomers. And then state the observation. I already know the observation, expected observation, that's just your memorization of the test, how well you know your test. Orange solution turns green. But which now is how well can you spot which ones are they? Well, if I look at P, that's not gonna be able to react to that. That's a tertiary alcohol, I'm pretty sure. Look at here, that's primary, that will. I look here, that will. That's a secondary alcohol. I look here, that's secondary alcohol. I look here, well, that is obviously an aldehyde, so yes, that will. And if I look here, that's a ketone. And ketones don't react with acidified potassium dichromate because you can't oxidize them. So it can't be that, it can't be that one. So it's going to be QRST. QRST, perfect. orange solution turns green. And then it says identify the isomer that react with Tollens region, state expected observation with Tollens region reacts. So now I'm gonna how to get rid of these. Let's get rid of that. How many questions are there on these? Okay, there's a lot for this. So let me fill in this again. P, Q, no, not P. Definitely not P. Q, R, S, T. Q, R, S, T. Q, R, S, T. Identify the isomer that react with Tollens region. With Tollens region, remember with Tollens region, it's only for aldehydes. To distinguish between aldehydes / ketones. But remember, ketones don't react with Tollens region. So the only thing that can react with Tollens region is an aldehyde, and therefore it must be T. And silver mirror. Silver mirror. Then it says identify the isomer that would react with ethanoic acid. Ethanoic acid, what is that? That's a carboxylic acid. Carboxylic acid. So which one will react with the carboxylic acid? Well, it's going to be the alcohols. Definitely not the aldehyde / ketone. No, the alcohols, because remember, carboxylic acid plus alcohol to form your ester. So it's just going to be all the alcohols. So P, Q, R, and S. Where is it? Yeah. P, Q, R, S. Suggests a simple way to detect if the ethanoic acid reacts with each isomer. Well, because an ester is formed, like I stated, carboxylic acid plus alcohol ester, esterification reaction, heating carboxylic acid with alcohol in presence of strong acid catalyst, the ester is going to have a sweet smell. So sweet smelling liquid. And don't even need to say that. You can just say sweet smelling or sweet smell. Give a reason why the mixture is poured into sodium hydrogen carbonate solution to react with excess acid. To react with excess acid, or we could say / to neutralize. State this type of structural isomerism shown by isomer P, Q, R, and S. Structural isomerism. Position, because all I've changed is a position, right? So it's just going to be a position. It's a type of structural isomerism shown by isomer P, Q, R, S. Describe fully how infrared spectra can be used to distinguish between isomers R, S, and T. Well, isomer R has an OH group, isomer S, same, isomer T, a carbonyl group. So I would say, I look at the data book. It tells me, alhamdulillah, to use the data booklet table A. So I go to that. Data sheet, table A. I know carbonyl group 1680 to 1750. So I know T has C10 P at 1680 to 1750 centimeters to power -1, whereas S and R have a OH peak at 3230 to 3550 centimeters to power -1. Again, all of this information of centimeters to power -1 comes from table A. And then I could say, well, R and S both have a unique fingerprint region. Fingerprint region is the region below 1500 centimeters per -1. And then what I'd say is compare to a database compare to a database and look for an exact match. So T has a peak at that, Right, SNL has a peak at that. Okay, that's fine. So I can identify T very easily to distinguish between isomers R, S, and T. But how would I be distinguished between R and S? Because both of them have the same peak. Well, then in this case, then I see R and S both have a unique fingerprint region / region below 1500 centimeters to the power minus 1. Compared to a data book and look for an exact match. That's it. Compared to a database, not data book, compared to a database and look for an exact match. Say by mass spectrometry using electrospray ionization is not a suitable method to distinguish between the isomers. All have the same MR. The isomers all have the same MR. Describe destruction of the missing from step 4 the method. The idea of place a weighing bolt, record a mass, tip in the conical flask, reweigh the weighing bolt. Reweigh the empty bolt, not the weighing bolt, in order to calculate the exact mass of what I did. You have to be very specific to the question, otherwise it's not going to give you the mark a lot of the cases. To calculate the exact mass of what am I looking for? Exact mass of salicylic acid, because that's grams. So exact mass of salicylic acid added to the reaction mixture. Reweigh the empty bolt in order to calculate exact mass of salicylic acid added to reaction mixture. Then it says suggest a suitable piece of apparatus to measure out this in step 5. Burette, perfectly fine. Measuring cylinder, pipette, burette. Identify a hazard of using concentrated phosphoric acid. It is corrosive. Anytime you say identify a hazard, a lot of the times it's just due to it being corrosive. Then it says complete the equation with ethanoic anhydride. So CH3 CO and then brackets 2O, and in this case I'm going to form CH3 COOH, ethanoic acid. Yeah, ethanoic acid, that's what I'm going to form, and this because CH3CO, 2 of them, and then your O on the outside, and CH3COH. It says, show by calculation which region is in excess, calculate mass in grams of aspirin produced. So first thing I'm going to do is I know 6 grams of salicylic acid react with this much ethanoic anhydride. Density of ethanoic anhydride is that. So first thing I would do is find out the moles of salicylic acid by just doing mass over MR. So 6.01 divided by 138.0. Then I would work out the moles of ethanoic anhydride, and remember, label them. Tell the examiner what you're finding out the moles of, because just tell them what you're finding out the moles of, because they might be confused and then they might not give you the marks. Moles of ethanoic anhydride. Well, first thing I'm going to do is I know density is mass over volume. Therefore, mass is density times by volume. And I know the density of ethanoic anhydride is 1.08. And I know the volume is 10.5. So it's going to be 10.18 times by 10.5 times by 1.08 divided by the MR, because that's mass, 102. Okay, so moles of salicylic acid, you get that, which is 4.36 times by 10 to the power minus 2. Then this case, you get 1.11 times by 10 to the power minus 1. Which one is in excess? Well, it's clearly going to be this, the ethanoic anhydride, because that's a bigger value than this. You might be wondering 4.36, 1.11, but this is 10 by 10 to the power minus 2, so there's 0.0. No, in this case, it's just 0.0. For example, so I'd say then the ethanoic anhydride CH3CO bracket 2O is in excess. Oh, it says put it here. CH3CO2O. And then it says calculate mass of aspirin produced. But then to find out the mass of aspirin produced, moles is mass over mR. Mass is going to be the moles. Which moles though? Is it the moles of salicylic acid or is it the moles of ethanoic anhydride? That again will probably trick a lot of students out. But the idea that if the moles of ethanoic anhydride is in excess, that's the one in excess, CH3CO2O. I don't care about that then. I'm going to be using ones that's not in excess. So therefore the mass is going to be the moles, which is 4.36 times by 10 to the power minus 2. The one not in excess, the moles of salicylic acid, times by 180. Yeah, so but I remember here it says the yield of aspirin is that, so then I need to times it by 84.1 divided by 100. And I get 6.60 grams. It's 6.59 grams. Okay, so moles of salicylic acid, moles of ethanoic anhydride, ethanoic anhydride is in excess, pretty simple. Then I don't care, therefore I don't care about the moles of ethanoic anhydride, I care about the moles of salicylic acid. Use the moles of salicylic acid to calculate the mass. I calculate the mass, but then I realized in the question it says the yield is 84.1%, so therefore times by 84.1 divided by 100, because that's the yield, or 0.841. So there's two ways in which melting point of crude aspirin collected would differ from the melting point pure aspirin. Well, this one, the value would be lower, and there'd also be a range of values. Value would be lower, the melting point, aka MP, would be lower, and value lower, range of values. Describe two important precautions when heating a mixture of ethanol and crude aspirin. Well, ethanol is flammable, so use a water bath to heat. Do not heat using a Bunsen burner. And now another precaution is heat to temperature below boiling point of ethanol. Below boiling point, so ethanol does not boil away. Explain purpose of adding a small amount of cold ethanol to remove any soluble impurities. To remove any soluble impurities. Describe one difference in appearance you would expect to see between these two solid samples. Crude oil is kept purified. Pure product will have larger crystals. That's it. Okay. Next question. Define the term electronegativity. The relative tendency of an atom to attract a pair of electrons in a covalent bond. You have to say that as well. So relative tendency of an atom to attract a pair of electrons in a covalent bond. For 1 mark, and then it says explain polarity this. Well, the idea that Br is more electronegative than carbon, well, that's very, very simple to state. Br is more electronegative than carbon. And what does that mean? Well, therefore Br is partially negative. carbon partially positive. So definition of electronegativity, relative tendency of an atom to attract a pair of electrons in a covalent bond. Br is more electronegative than carbon, therefore Br is delta negative and carbon is delta positive. Outline the mechanism for the reaction of 2-bromopropane with excess of ammonia. So methane for 4 marks. Okay, let's carry on. Methane, ethane, propane, bromo. So let's just say here, put it here, and let's get into the mechanism now. Once I've fully drawn it. So excess of ammonia is obviously going to be nucleophilic substitution. Lone pair of electrons NH3, 2-bromopropane, attacks partially positive carbon, CBr bond breaks. Very simple. But obviously that wouldn't be for 4 marks, right? There's another step as well. It's an excess of ammonia. So it's not just one ammonia molecule using 2. So then I've got my NH3 nitrogen positive. Then what I would do is then draw that out again here. Nitrogen positive charge, and then what happens is another ammonia molecule is like, you know what, let me join in as well, and this case it acts as a base, takes a proton, and then you go to here, and then what you get is this hydrogen, lone pair of electrons, NH2, and there you go. So did it say for skeletal formula? Because in the mark scheme it's skeletal formula. It didn't. So yeah, mine's completely correct. There you go. Takes proton, there you go. And then you've got NH2. And don't forget your NH4 plus ion. But it will bond with the Br with the minus lone pair of electrons. So NH4 Br. For 4 marks. Then said draw skeletal formula of the main organic species form the reaction between a large excess of 2-bromopropane and ammonia. The skeletal formula of the main organic species. There you go. And the use cationic surfactant. Cationic surfactant. State the type of reaction in step 1. Identify the region and conditions needed for step 1. State the type of reaction step 2. Okay, so for in step 1, it's going to be, acylation. Acylation. Identify the region CH3COCl and AlCl3 catalyst. It's in the mechanism for the reaction in step 2. And step 2, I'm going from this to this. So what I've done is I've added a hydrogen here, and I've added a hydrogen here. It's going to be nucleophilic addition. Nucleophilic addition. Nucleophilic addition. Identify the inorganic reagent, sodium borohydride, and the name of the organic product. The name of this, 1-phenyl ethane 1-ol. Ethane 1-ol, sorry. ethan -1-O. So acylation, HCH3COCl, ethanol chloride, AlCO2 catalyst, nucleophilic addition, sodium borohydride 1-phenol, ethane 1-1O. Organic product of step 2 is reacted with concentrated ferric acid. Step 3, outline the mechanism for step 3. So this is concentrated ferric acid. So I'm going to draw that out first. So I've got this, and then I've got CHOH. I'm just going to put it here. Yeah, it's supposed to go there. CH3, and then the OH. Concentrated sulfuric acid. So it's this is not an alkene. I was thinking of alkenes reacted with cold concentrated sulfuric acid to form alkyl hydrosulfates and alcohols. That's not going to be it because it's already an alcohol. So it's going to be the other one, which is, oh yeah, because I'm going from this alcohol to this alkene, elimination of water. So it's a dehydration reaction, elimination of water, and again we use concentrated sulfuric acid or phosphoric acid. So what's going to happen is the lone pair of electrons here, H2S4. Well, let me draw that out. Hydrogen O S double bond O OH, and what happens is it goes to here, which is partially positive, it's partially negative, and then it transfers electrons to here. Then what happens is, let me zoom out a bit. Obviously, sorry for the bad drawing. And then you get this. That is a CH, right? Yeah, that's a CH. CH3. And then you've got this oxygen. Yeah, then you've got the CH, and then you've got this. Sorry, this water molecule now. Oxygen is positively charged. You got your CH3, and actually now I should need to draw them out. Splayed formula properly. There you go. And then what happens is this, now the carbocation feeding here, that leaves. And then what happens is then this is positively charged. I'm going to go through the individual steps. Then this is positively charged. So CH, this carbocation's here, and CH3. And then from here to here. And then that's how you form that double bond CH, and then you lose that H plus, and then you get CH2. Okay, so lone pair electrons and the oxygen H plus bonds to that hydrogen positive, transfer electron to oxygen delta negative. You get that, and then it wants to leave as a H2O molecule. That's fine, and then form the double bond. Draw the structure, draw the repeating unit of polystyrene. The repeating unit of polystyrene. So that's this polystyrene, the repeating unit. The first thing I need to do is put it in this format. No double bonds. And then just fill in what I've got. I've got hydrogen, two hydrogens. And then I've got a hydrogen here. And then I've got a phenol group attached to it. There you go. So remove the carbon-carbon double bonds and then just add these sticks on the outside of it. I can't go through this in a mass spectroscopy. I can't go through that, and yeah, I can't go through that. Can't go through that. I think there's yeah. Okay, question 8, and then question 9. That's it. Okay, that's perfectly fine. Question 8. Question about citric acid, a hydrated tricarboxylic acid. Its formula can be represented as H3Y X H2O. A 1.50 gram sample of this contains this much oxygen by mass. A sample burns completely inert to form this much carbon dioxide, this much of water. Should empirical formula is that. So um uh so I would just again do what we normally do. The CHO, find out the moles, right? The first thing I need to do is I can find out the moles of CO2. The CO2, which is mass 1.89 over the MR CO2, which is 32 plus 1244. That will give you 0.043 moles. Then I can work out the moles of H2O, which is 0.643 divided by 18. Even if you don't know what you're doing, you can get easy marks by just working out the moles. So 0.0357, 2 marks already. Then I can work out the moles of hydrogen by doing 0.036 times by 2, because 1.50 minus 0.913 is 0.036 times by 2, which gives me 0.0714 moles. And then I can work out the moles of oxygen. 0.913 divided by 16, obviously 0.057 moles. So even if I didn't know what I'm doing, I've already got 2 marks out of 5, which is better than leaving it blank. Short empirical formula is that. Well, first thing I'm going to have to do now is, because now that I've got the moles of CO2, moles of H2O, moles of oxygen, moles of oxygen, and I can say, well, C is 0.043, H 0.0714, and then the moles of oxygen 0.057 divided by the smallest number 0.043, 0.043 divided by 0.043, and you get the point, and then you get to this as your empirical formula. A 3.0 gram sample of this, it's heat to constant mass, and hydrogen this has a mass of this. Show using this data that the value of X equals 1. So 3 gram sample of this, so what I do is find out the moles of H2O. And how do I do that? Well, it's going to be the mass of the moles of this divided by the MR, and therefore to find out the MR of H3Y, is just going to be the moles mass of MR masses. Moles is mass of MR is mass divided by MR is mass divided by the number of moles, which is that 3 divided by 2, 110, and then you should get x equals 1. So find out the moles of this, mass of MR, then use, because moles is mass, because I'm trying to show x is equal to 1, so I'm trying to show that the MR, I'm trying to find out the MR, so then I can work out the MR, mass over moles, and then I can then realize the MR I get as 192, and the total MR is 210. I do that, I get 18, and that's already 18, so therefore it's 1. Question 8.3, complete this IUPAC name for H3Y. It's going to be 2-hydroxy. 2-hydroxy because I've got a hydroxy group and a second carbon. The number of peaks, again, I haven't gone through this. And then question 9, calculate the amount of A and the amount of B in equilibrium mixture. An aqueous solution containing this much add to this much. Okay, so I would always use the ice method. A, B, C, I, C, E. And the more you practice the ice method, the faster it gets. So 0.25 initially, and 0.25 initially, 0 initially, and I've got 0.015. So I've added 0.015. So I'm going to do on the left hand side minus 0.015. What I'm going to do to this minus 0.015 times by 2 because it's a 2 to 1 molar ratio. So 0.25 minus 0.015. 0.235 of A, 0.235 for A, and for B, 0.25 minus 0.015 times by 2, 0.22. 0.235, 0.22 moles. Then it says different temperature of the equilibrium mixture between this much, calculate value of Kc, just the units of Kc. So first thing I would do, I know Kc is square brackets, and let's construct the equation for Kc. So I know I'm working with products over reactants A times by B squared. Kc equals, now in this case the volumes will cancel out because the Kc is not on this side, but there was a question, past paper question a couple of videos ago, which I did it all today, all these videos on paper 2, that was like calculate value, a concentration of something, and I got Kc here, and then I assumed volumes cancel out, but in reality they don't because of the Kc was next to the concentrations. In this case the volumes will cancel out, but I'll just show it anyway. So 0.020 divided by 350 times by 10 to the power minus 3 divided by concentration of A, 0.30 divided by 350 times by 10 to the power minus 3 times by 0.020 divided by 350 times by 10 to the power minus 3 squared, since there's 2 moles of it. Okay, so 0.020 divided by 350 times by 10 to the power minus 3 divided by 0.30 divided by 350 times by 10 to the power minus 3 times by 0.020 divided by 350 times by 10 to the power minus 3 squared. And I get Kc as 20. Okay, something's gone wrong. 0.0. Why did I write 0.020 here? That's 0.025. I must have misplaced it. 0.025. And I get it's not even 0.0, it's 0.25. just silly mistakes, which are very easy to make in these type of questions. 0.13. Now the units, well, I've got multiplicative minus cubed on the top, right? Multiplicative minus cubed over multiplicative minus cubed. That'll give me 1 over multiplicative minus cubed squared, which is the same as 1 over multiplied minus 2 dm to the power minus 9. No, not multiplied minus 2 dm, because that would be multiplied power 2 dm to power minus 6. But then, because 1 over is multiplied power minus 2 dm to the power 6. And KC is 0.13. Didn't really make any mistakes, except for just silly errors, but that's fine. So just why expression for K can be written without concentration of water. Let's find out. The idea that the concentration of water is effectively constant, because it's so much, because so much bigger than other concentrations. The concentration of water is effectively constant because so much bigger than the other concentrations. Then it says distilled waters add to this much of chloroethanol to make this much solution. Mixtures allowed to reach equilibrium. Value of equilibrium constant K is that. Calculate equilibrium concentration of this. So first thing I would do is rearrange it. So I know ClCH2CH bracket OH squared concentration equals K times by ClCH2CHO, and I know K is 37.0 times by this. Well, it's 5 marks. It's not going to be that easy, right? Reason being is because I'm going to have to probably, I'm assuming, some algebra, which is fine. So first thing I'm going to do is find out the moles of chloroethanol. So moles of chloroethanol 4.71 divided by 78.5 to make 50 centimeters cubed of solution. But that's initially. Mixtures allowed to reach equilibrium. That's why it's going to be so much more difficult. So what I'm going to use now is, I get the answer for this as 0.06 initial moles, but I want the equilibrium moles, right? So how do I get from there to there? So I'm going to use the ICE method, ICE, and I've got, and the thing is that's really annoying is these are really large, like they're not simple compounds. I have to write them like this as well. And then the other one, ClCH2CHO 2CHO. And I know that initially of chloroethanol, yeah, I've got 0.06. Therefore, the equilibrium moles, well, I'm gonna I'm going to minus x, so it's going to be 0.06 minus x, and therefore the equilibrium moles of ClCH2CH is going to be equal to this, or which square is going to be equal to x. Now I'm using x and minus x, I can somewhat find something now, I can work with something, therefore I can say 37 equals x over 0.06 minus x. And obviously the volumes, but the volumes will cancel out anyway. So yeah, times by this, so I get 37 bracket 0.06 minus x equals x, and then expand it, 37 times by 0.06, 2.22 minus 37x equals x. Therefore 3.22 divided by 38, 0.05842, but that's not the final answer, because remember, then I want to find out the concentration, so I do need to divide it by the moles, the volume, because moles concentration, volume concentration, moles divided by the volume, which is 50 times by 10 to the power minus 3, and then I get 1.17. So I'd say this is pretty nice. This part's pretty nice. I'd say this part again, yeah, very nice. I just made a silly calculate error by not reading the values correctly. This pretty nice as well. This bit, no, it is very difficult. It's just not, a question I've really seen before. So firstly, find out the moles of chloroethanol, and then realize these are the initial moles. Then it says the mixture is allowed to reach equilibrium. I want to find out the equilibrium moles, right? So I'm going to say I'm going to let equilibrium moles of this equal x, and therefore the equilibrium moles of this. Well, if that's x, that's going to be 0.06 minus x, because we don't care about this really, because it's effectively constant because it's so much bigger than other concentrations. So if that's going to be x, which it will be, that's going to be 0.06 minus x. That makes sense. Then construct the equation. K is 37 equals x over 0.06 minus x. Show the cancelling of the volumes. And then rearrange it. Expand the brackets. You get x is equal to something. And then divide by 2.22 divided by 38. You get x is equal to your value, right? And then that is moles. The whole thing we did then, the ICE method, is used to find out the equilibrium moles, not the concentration. Therefore, the moles concentration, volume concentration in moles divided by the volume, 50. I want it in moles per dm minus cube, so 10 by 10 to the power minus 3, and then I get 1.17. So definitely not an easy question. If you guys didn't get it, go for, yeah, I understand it is. If you could, definitely one of the trickier KC kind of questions. And yeah, that's it for that part. Didn't miss anything. Then it says complete the mechanism. Complete the mechanism by adding 2 hours, and it's a nucleophilic addition mechanism. So it's not nucleophilic addition elimination, so that's fine. Well then, so then we've got lone pair of electrons here, minus charge, and then what happens? Well, you're not forming a double bond that leaving, because that's nucleophilic addition elimination. That's definitely positively charged. Goes here. Then what happens is you've still got your lone pair of electrons, negative charge, bond to the H plus. So lone pair of electrons negatively charged, then that leaves this OH, middle of the OH oxygen leaves, and then it bonds to H plus lone pair of electrons minus charge, and then you get that. Suggests when excess water is added to ethanol, similar nucleophilic addition reaction occurs. Explain why this reaction, suggest why this reaction is slower than reaction question 9.5. All right, it's about the alkyl groups and all of that. So the carbon, just saw in the mark scheme. Carbon in the carbonate group is less electron deficient because the CH3 is electron donating slash CH3 has a positive inductive effect, so higher activation energy, therefore slower rate of reaction. Whereas with this, you haven't got an alkyl group. No alkyl slash CH3 groups. Therefore, no positive inductive effect. It's not going to be electron donating. Therefore, lower activation energy. But it says suggests by this reaction slower because the carbon in C double bond O is less electron deficient because the CH3 is electron donating slash CH3 has a positive inductive effect, so higher activation energy, therefore slower rate of reaction. And that is the end of this paper.